Patrick Pantel. Patrick got his Ph.D. in 2003 from the University of Alberta. Now he's a research scientist at ISI. He has done seminal work with Jack Lane on word sense induction, and also he's working on text mining. And I have used some of his algorithms in my research as well. So Patrick?
Thank you very much. So it's my real pleasure to be here with you guys today. It was really nice when I landed 2 nights ago to feel the brisk wind again hitting my face. So I grew up in central Canada. Yeah, so I grew up in central Canada, and when I moved to Edmonton, it was actually much balmier weather for me. And so the weather in Edmonton is about, at this time of year, maybe 32 on a high. It's very, very cold. It's already snowed about a month ago. And so that was nice for me. So this is even better for me. And LA, I miss the seasons. So it's nice to come here and see the colors in the leaves. So you guys are really lucky to be here. So today I want to talk to you a little bit about the work that we're doing at ISI on semi-automatic ontology construction and the different facets that people are working on and what I'm working on specifically. So let me start by giving you some examples of an NLP application where we're getting some errors that maybe an ontology would help. So here's in QA, here's the type of answers that we sometimes get for where are zebras most likely found? And the answer the system got was in the dictionary. So clearly somewhere it said that zebra is one of the last letters in the dictionary or something like that. How many people live in Chile? 9. Okay, so you can imagine a text, 9 people in Chile died or something like that. What is an invertebrate? Chicago. Okay. So these answers are not good. So clearly we need some kind of common sense semantics. We need some information about numbers, or we need an ontology, it might help. So it turns out that ontologies have been shown to be useful in some applications, and I think that in the future, hopefully we'll have even more.
Define ontology.
Excuse me?
I wish you would define ontology.
Okay, so in my talk, I have a very loose definition of ontology when I work with it. Essentially, I'm looking at hierarchies of concepts and relations between them. So WordNet is an example of the type of ontology I'll be talking about today. I know that in knowledge representation, ontology can have a very different meaning. But I'm going to mean here the WordNet type of ontology that you would work with in NLP. So some example applications where ontologies have been shown to be useful. So in IR, between Trek 98 and Trek 2001, we saw about a 40% improvement by trying to understand the query and expanding query terms according to that query. In QA, by trying to understand the Q and understanding the A, and then matching the meanings, we saw a huge improvement in accuracy. And hopefully in conceptual summarization, which is work that's being done at ISI by Chin-Yu Lin and Ed Hovey, there they want to try and interpret the topic at a conceptual level and then fuse those concepts and then regenerate a summary from that conceptual level. So that hasn't been done yet, but hopefully it'll be done soon. So then what's the vision? Essentially, what we have is we have all kinds of broad coverage semantic resources out there, like WordNet, which are useful in some applications, but they do have some problems. So, for example, one big problem about WordNet is that it's very prescriptive. And what I mean by prescriptive is that you'll rarely find semantic relations that are plausible but not necessarily guaranteed. So, for example, you'll see that a dog is an animal in WordNet, but you won't see that dog is a pet. Even though this happens sometimes, a dog is not always a pet. So you tend to not find these relations in WordNet, but they might be useful in certain situations like QA. Another problem is that these resources have limited coverage. In WordNet, again, one big problem is it has poor proper noun coverage. It does have some proper nouns, but it's very poor in that. And these resources are also, since they're manually done, they're very hard to update, and they're hard to adapt to new domains. So can we then try to semi-automatically build or extend these resources? Or at least try and extract some information that can help a human in increasing the coverage of these resources. So an advantage of doing, say, a corpus-based approach to building ontologies would be that you then get some corpus-motivated reasons for finding a new concept or for attaching it in the ontology in some particular point. So if you look at WordNet sometimes, you look at the attachment where a concept is in the hierarchy, And it's questionable sometimes why that concept belongs there. And at some point, somebody made a decision of why this concept exists and why it's attached where it is. But over the time, sometimes that meaning gets lost, and I don't know myself why a particular decision was made. But what would be nice in a corpus-based approach is you'd have a corpus-based justification for a particular attachment. So you might say that this concept belongs there because it behaves in text in a particular way. So that could be some useful information. And one big advantage is that if it's semi-automatically done or automatically done, you could greatly increase the speed at which you can update or adapt these resources. So in this framework, what is the work that's being done at ISI? There's a lot of parallel projects being done on the topic. The first one here is work that's being done with ISI, PEN, and BBN. And essentially, it's trying to do, again, some manual work, trying to extend ontologies. In the context of the OntoBank project, what they're trying to do is take an ontology like WordNet and try and find the proper coarseness level, a coarseness level where users of this ontology would find it useful to know the particular sense inventory or the relations in the ontology. So the way that they do this is they take a particular sense inventory as it is in WordNet, and then they have a bunch of annotators sitting in a room that then annotate some text according to the sense inventory. And if the agreement between the annotators is high, then the coarseness level is probably correct. But if it's low, that means that you might have too many senses. And the hypothesis is we should try and merge some of these senses and then do the test again until that you get agreement between the annotators. There's been some work on merging and alignment of ontologies. This project is not currently, it's done right now, but essentially what they try to do is take a bunch of ontologies like WordNet, Microcosmos, and other sources of knowledge that were accumulated and try to merge them into a meta-ontology, which we call Omega. And so there you have problems of how do you align the knowledge between the ontologies and how do you merge them. So we've also been doing some work on harvesting new concepts, harvesting instances of concepts, and harvesting relations between concepts. So this is where I'm particularly interested in. So there's been some work on doing pattern learning. So Deepak Ravichandran is a student of Ed Hovey, and he's been doing a lot of work on trying to learn patterns that can help you then retrieve things like biographical information. There's been some work on clustering, on discovering new concepts by clustering, or discovering relations by doing corpus or web-based mining. And then there's a nice area, I think, of validation, which is very important, and not much attention has been spent there. And how do you validate an ontology? The knowledge that is in there, is it still trustworthy? Is it current? So over time, some knowledge might have to be taken out of the ontology. Is the knowledge a fact or an opinion? This is a new area of research that we're trying to delve into at ISI. And let's try and determine what statements are facts, which ones are opinions. And if they're opinions, what kind of opinion is it? Is there a positive sentiment, a negative sentiment? So I think this is some interesting work. So you might not want to include in your ontology information like Bush is an idiot, because that is probably an opinion, though it depends on what you think. And finally, one interesting area of research that I'm looking at is once we've mined information like new concepts or new relations, currently this has been done at the lexical level. How can we take the semantic information that people are harvesting and insert it automatically or semi-automatically into an ontology? And today's talk, I'm going to speak about some of this harvesting of relations and also this bottom point, how do we automatically incorporate harvested knowledge into an ontology? So let's look a little bit more into the harvesting of concepts and the harvesting of instances and relations. So the work that I've been doing in this field, I did my PhD work on trying to discover concepts in text in an unsupervised manner and try to induce some senses out of it. So there was a clustering algorithm, CBC, that we developed that tries to do this by trying to discover groups of words that unambiguously describe concepts in the space of words. And then tries to find senses of words by figuring out which concepts a word belongs to. There's been some work also on finding, on extracting paraphrases or expressions that have the similar meaning. So this was an algorithm that we had called DIRT. I did this with my, my thesis advisor. And here what we want to do is find paths between between words, so find expressions between entities, and find other expressions between entities that mean the same thing. And this was kind of a neat approach. So the typical approach to that we use when we do distributional similarity, when we want to find which words are similar to other words, we take a bunch of words in text and we find some features for these words, whether it be the words that occur near them or whether it be grammatical relationships that this word appears in text. And then you get this big vector of features for each word, and then you can just compute the similarity between the vectors, how close the vectors are to one another. So in the work on paraphrasing, we kind of flip that view around. So instead of our elements being words and the features being these grammatical relationships, we had the elements being paths in a dependency tree that join two entities, and then we had the features of this path being the words that can occur on either side of the path. And then we could apply the same methods, the same distributional similarity approach, to find similar expressions, or expressions that occur with similar entities on each side. Some other work that we've done is on extracting conceptualizations. I'm not going to talk much about that now. But in today's talk, I'm going to talk about a system that we created for trying to extract, it's a first step toward trying to extract verb relations by mining the web. So it's an automatic method for finding finer grained relationships. We have about five relationships that we find between verbs. And I'll also be talking about, once we have harvested this type of information, how can we try and get it at the ontological level? So that's some current work that we're working on now. Okay, so stop me anytime for questions. The talk is going to be pretty top-down, so I'm going to start by giving you what do you get out of this system we call Verb Ocean, which are these relations between verbs. So what Verb Ocean is, it's a network of verbs, and currently we have about 3,400 verbs, and the edges in the network represent a semantic relation that joins two verbs. So the types of relations that we find are things like similarity, strength, which I'll describe in a minute, antonymy, enablement, and temporal precedence. The resource is available for download and available for querying. There's a nice demo where you can have graphs being dynamically generated. When you give it a verb, it'll find all the relations and show you it in a nice graph. So that's the resource. And what was the lesson learned? The lesson learned was that these relations do exist on the web, and they are extractable by applying simple patterns, which is not something that we were able to do at a corpus level. So the patterns that we're finding to be able to do this don't hit that often, and you don't have enough text in 10 or 15 gigabytes that we tested on to be able to do this at the corpus level. But at the web level, we're able to do it. But there are all kinds of challenges that you have to deal with when you do it at a web mining level.
We're going to illustrate the relations you listed on the previous slide.
Yes, right now, after this slide. So let me first give you an overview of the approach. So we're extending previously common known approaches for extracting relations, which typically have been done between nouns. So it's a pattern-based approach. So typically people have used this to try and extract things like is-a relations between nouns or part of relations between nouns. And the idea is you define a set of patterns that can extract this information. It's just a standard IE problem. And then you apply the patterns to text, and then you find the relations like is-a relations. The difference for us is we're doing it on a web level, on a scale of the web. So there are some challenges, like we cannot part a speech tag all the web. So we have to be a little bit clever in how we estimate some counts, which I'll show later. And some differences of our system is that we use patterns that indicate verb conjugation. So this increases the expressiveness of our patterns. And the measure that I'll show that we use to determine how well a relationship holds between a pair of verbs is using a type of mutual information scoring. So I'm going to go through each of the 5 relations that we discover in Verb Ocean. And I'm going to show them all by giving you an actual example out of Verb Ocean. So this is the type of output that you get if you go to the website and you type in the word berate, and then you ask for its similarity at a depth of 2 here, or 2. And then it'll just generate this graph for you. And
Google will generate.
Excuse me?
Google will generate.
So each of the relations here will not be dynamically generated on this website. So it has to be a verb that we have in our system. So we have 3,400 nodes. It's pre-computed. And then you can query it. So this is essentially is just querying what we've pre-computed.
So what has that got to do with Google? I'm sorry.
So each relation that we got here, so there's a link between berate and admonish.
Yeah.
And this is a similarity link that was discovered by mining the web. And I'll show that how we did that in a second.
So you gave berate to Google and then
We gave the
admonish to
pair.
Google and-
We gave the pair to Google. We said, is there a relationship between berate and admonish? And then our scoring method returned, yes, there's a similarity relationship. It could have said there's no relation, or it could have said it's a temporal precedence relation. This is the type of output that we get.
What is it that it could have said? Who is it?
The system,
It is
which
a big
queries
system. It has nothing to do, still nothing to do with Google.
the system that, absolutely. So the system that we developed is a web mining approach that uses Google. It could use a different indexing, but as I'll show, we currently use Google to get the information we need.
The Google part is that we wanted millions of users of berate and millions of users of admonish, so that we can figure out.
And I wanted to test patterns to see how often did berate and admonish happen in a pattern like X, i.e., Y, something like that. So I can query Google for that. I'll explain that in a second. So here are some other relations that we discovered. The strength relation is a subset of the similarity relationship. And all we're trying to find here are verbs that are similar but have a more complete or more comprehensive action. So for example, the system discovers that terrorizing is stronger than attacking, which is stronger than intimidating, which is stronger than harassing. Another example here is dwarfing a problem is stronger than surpassing it, which is stronger than hitting the mark, which is stronger than approaching. So one thing you'll notice in these graphs is there's a lot of room for improvement. And since, for example, this relationship here is, since we see that dwarf is stronger than surpass, which is stronger than hit, stronger than approach, we could infer that dwarf is stronger than approach because of the transitivity of the relationship. Taking apart the sense drift, there's a sense drift problem. But you could look at these graphs after the fact and do some post-analysis to be able to improve the networks. But as it stands now, each link that you see in the graph was obtained by just looking at the pair of verbs that the link connects and asking the question, what is the best link here? After the fact, you could look at the whole graph and determine and clean it up or find new relations. Is there
So
a
on the
question?
left graph, you actually got the transitive closure for free.
Yeah, here, so it actually,
On the right graph, you
that's right. On the left, it actually found the closure, but on the right here, we could infer it. Is there a question back there?
So yeah, so I guess to go back to something you may have described before, the features for each verb, is that basically the subject of the object?
No, so here we're not using any feature representation like I have in my previous work. It's actually just looking for it. The way it'll find these relationships is just by looking at strict surface patterns on the web,
So,
which I'll explain in a minute.
so these things have, okay.
Yeah,
So you're basically taking the results and using simple rule-based information extraction.
exactly,
Okay.
exactly. Instead of finding typical IE things like who did what, we're actually finding relations,
Gotcha.
semantic relations. Yeah. So this is the one that we do the worst on, antonymy. And I think it's because we haven't come up with a good set of patterns to search the web for. But there are different kinds of semantic opposition, and we just lump them all into one. We don't actually distinguish between the different types of antonymy.
So you're in a triangle here, which I guess is.
Yeah, here's another, that's right. So you see another problem here, there's a loop here. Post-analysis, again, we could look at this and we could say, what's the weakest link here, and take that off, because we know this is impossible. So again, each of these decisions are made on a verb pair case. Enablement is a relationship that it turns out we don't get many of these out of the system. I'll give you an idea why later. But the type of relationship that we mean by enablement is if you have a pair of verbs, V1, V2, then we ask the question, can V1 result in V2? So you click, then clicking might enable scanning or configuring or uploading, things like that. And finally, the last relationship is temporal precedence, or a happens before type of relationship. So, so these asymmetric relationships, like temporal precedence or the strength relationship, we end up doing a little bit better on. And the reason is because the asymmetry gives us an extra test that we can do later in the pattern-based matching, which I'll show in a second. But here, an example, you see that you first design, and then you test, and then you patent, and then you manufacture. So it finds these types of temporal relations. Okay, so how do we do this? The first step of the approach is to find seed verb pairs, to find the verb pairs that we want to test. So there are, in WordNet, about 11,000 verbs or so. So we could look at each of those 11,000 verb pairs. But it turns out that there's no way we can do this. We have a limitation, because we're using Google, querying Google, we have a limitation on how many queries we can do a day. So instead what we did is we found a set of verb pairs that we know have some kind of association by using our previous system, DIRT, that I explained before. So DIRT gave us expressions that have similar meaning. So we might be, so by looking at verb pairs that come out of DIRT, we're more likely to not waste our tests on Google than if we just randomly chose verb pairs. So we're going to get more relations by starting with good verb pairs. So the number of verb pairs that we ended up having were about 30,000 or so verb pairs out of this system. And 30,000 verb pairs took about 40 days to process. Again, it's not because we don't have the processing power, it's because we can't query Google in it. So if we index the whole web, we can do this a lot faster, which we are currently doing at ISI. We're currently crawling the web. So then, once we have these verb pairs that we want to test, so for each verb pair we ask the question, what is the relationship, if any, between the two verbs? So then what we...
I don't understand, what's the criterion that a pair of verbs is a verb pair?
So you could look at all possible verb pairs, 11,000 by 11,000 verb pairs.
Yes.
And that's ideally what we want in the end. But what I'm saying is that we cannot process that many right now.
Select the candidate?
So we could just have randomly selected 30,000 verb pairs.
Okay.
But then a lot of them, most of these verb pairs don't have any relation.
Yeah.
So we thought that that would be a waste of resources. So instead we said, can we take verb pairs that we know have some kind of association?
Yeah.
So we used this previous system called DIRT, which generated paraphrase expressions. So if you say X solves Y, it'll tell you X resolves Y. Is a similar expression.
That's what the DIRT does.
That's what DIRT does. But it doesn't just give you similarity. It gives you things that, it gives you phrases, all kinds of different things, but it doesn't just give you the similarity relationship. You get all these different relationships out of it. It's just, DIRT doesn't tell you what the relationships are. So we took those verb pairs as the initial seed. And when I said we don't get a lot of enablement relationships, I think it's because of this extracting from DIRT. When we just did a manual check of a sample of these DIRT relations, we rarely found an enablement relationship. So I think we might find more enablement if we saw the whole 11,000 by 11,000 verb pairs.
So Patrick, are you saying that you just search for the word solves or the phrase and then on Google and you look at the words on either side of that?
So what we do,
I'm not trying to see.
so what I'm going to show we do is we first find the verb pairs using DIRT. So DIRT, we look for all X verb Y type of patterns, and then we look at all its similar patterns, and we extract those as candidate verb pairs.
Yes.
And then we ask the question to the system, what is the relationship here, which I'll explain on the next slide on how we actually do this, and that should answer your question.
Oh, I see. Okay, so you don't look at any, you don't extend the DIRT set at all into
No.
the web.
No.
Okay.
Yeah. So then for each of these verb pairs, to be able to test it on Google, for each verb pair and for each possible 5 semantic relations that we're looking for, we assign to these semantic relations manually a set of patterns that we'll search over Google. Again, this is done manually. This could be done automatically later, but right now this was done manually.
So how many such patterns are there?
Next slide. Yeah, sorry, I'm top down. Maybe I should do bottom up. No, it's all right. That's the problem with top-down talks, I guess. So what we're going to do is we're going to test these patterns on the web, and we're going to use these to score our patterns and score the relationships. And once we get these scores, then we have to output a consistent set of semantic relations for the verb pair. So sometimes, for a particular verb pair X and Y, both similarity and antonymy will hit. You might argue that this is possible, but in general, we'll say that this is impossible. You can only output one of the two. The happens before relationship can occur with all the other relationships, but the other 4 relationships cannot co-occur. Okay, so what do the patterns look like that we're searching on Google? So the rows here show the 5 different semantic relations that we're trying to find. And in the first column, the number that you see in parentheses is the number of manually built patterns to search for that relationship. So for example, similarity, we built four patterns only. Enablement, we had 4. So then in the middle column, you see some example patterns that we'll search on the web. So for the bottom one here, happens before, one of the patterns we look for is to X and then Y, where X and Y are the slots for the two verbs you're testing for. And I'll show you this, how it fits into the actual formula for computing mutual.
You don't really go only after these bare phrases, right? I mean, you take it from a sentence and you...
We do not do any processing in the sentence. We actually...
None whatsoever. So it really has to be 2X and then Y.
Exactly.
It cannot be anything...
That's why it doesn't work on a corpus, right? Because these are very, very specific patterns. But the assumption is that over the web, somebody will have said this if there's a relationship. It might be an incorrect assumption, but that's what we're banking on. Yes, sorry.
On the similar, this is just for my own edification. Do you have a pattern like X, comma, Y, comma, and Z, or?
So Google does not index commas, punctuation.
Okay,
so we
that's
cannot
right,
use
right.
that. And same thing for part of speech, right? So we cannot force these things to be verbs. So if you're looking, you'll notice that this pattern here for enablement says X'd something by Y'ing the. So the things I want to point out here is that, so X'd with the ED forces our verb to be conjugated in the past. Okay, so we do verb conjugation like this. The star can be replaced by anything in Google, but the trailing the is important. Without that trailing the, you can actually match Y as a noun and not know it. So we're not part of speech tagging at all, but by adding the word the, we reduce the number of hits we're going to find, but we're still banking on the fact that somebody will have written this on the web for the verb pair, if it exists. Yeah, get in.
Two questions. The first is, can you really do the star in Google to replace a word?
You can do a star as in being any word, yeah.
Can you do it with multiple stars?
Can you put 2 stars in a row? I think so. Do we have a pattern like that? I'm not sure.
And you can do star, you do. I didn't know you could do you could do partial matches on words. How do you do X?
X. Okay, so we have a verb conjugation model that when we're testing for a particular verb, we check what's the past tense.
Okay, I'm sorry, of course.
So it's not.
For a particular verb.
Yeah.
And my second question was, how did you choose these 5 semantic relationships?
Okay, so why not more, right?
Or why?
So,
why not?
so we looked at what relations are in WordNet, and we tried to cover those. And then we saw what else we can get out of this. Like the strength relationship, we found cases where we can get. But what we really wanted was entailment. But we could not come up with patterns that gave us entailment. But now we're actually working on, given the output of Verb Ocean, how can we get entailment? And I think you can actually do it as a post-processing.
Do you know, one of Eugene's students,
Yes.
that I think his name was Sean Zeller. I don't know if his work was ever published.
Okay, great. So I know that Ido Degang also is working hard on trying to do automatically find entailment. There's this whole program over there, what is it called? I forget the name of the program, but there's a test being set up in a couple of months or so to try and extract entailment relationship. It starts with a P. I forget the name of it. It'll come to me. I'll tell you later. Okay. So then, the way that we obtain these patterns, again, I said it was done manually, but the approach that we did to get these manually could be done automatically, I think. So what we did is we took a set of 50 verb pairs and we tagged them with the correct relation. And then we searched on Google for all the documents that contain that verb pair. And then we just manually looked over the resulting documents to see what kind of patterns would give us a high recall and high precision on this small set of 50 verb pairs. And this took a long time. This was about a week's worth of time, or 25 hours. I think that's conservative. And we came up with these 35 patterns. Now, how could you do this automatically? There was a paper last year by Deepak Ravichandran, a student at ISI. He showed how you could automatically extract these types of patterns for biographical information. So what he did is he was trying to find what was the birth year of people. And he seeded the system with people and their birth year, like Mozart and 17, whatever he was born in. And then the system automatically went to Google, found the documents that had this pair, and then had a dynamic programming algorithm that would try and find patterns that would extract this information with high precision and high recall. So I think we could apply that here to do this automatically, but at this stage it's done manually.
Also, is the limitation you have with Google that, I'm so familiar with the Google API, is it just that the license only lets you do 1,000 queries a day?
Okay, so we have a license that allows us 25,000 queries a day.
Okay.
But there are all kinds of problems that came up while doing this with Google. I wasn't going to say this, but one of the big problems with Google is if you query the word apple and you look at the first 100 results, and I'm in LA and I query Apple at the same time and I see these 100 results, we're going to look at the same thing. But if you look at the oh, all right, that's Deepak. That's Deepak. Yeah, I just talked about you, Deepak. All right. Sorry about that. What was the question again? I'm sorry. What was it? Oh, Google. The Google problem. So if you look at the first 100 results of Apple, and I look at the first 100 results of Apple, we're going to see the same thing. But if you look at the last hits, and I look at the last hits, we might see different things. So it turns out with Google, when you query them, you might not hit all their data centers, depending on the load on the network. We'll always get the same first bunch of hits. Those will always be the same. But what we're interested in these patterns are how many documents in total on the web match this pattern. We don't actually look at the documents, but we want to know the total. And that number can change from hour to hour or day to day. So that becomes a big problem. So what we're doing now, we have friends at IBM Alameda. They have a web fountain project where they have the whole web indexed. And they're going to run our system on their index and see if that really made a difference for us. So this is just repeating what I said about trying to make our patterns so that we avoid finding nouns or incorrect parts of speech. So again, we had X something by Y and V. If we don't have that V, we might match on this first point here. So waved at by parking guard. If we didn't have the trailing V, we would match this. Okay, so how do we score this now? So essentially, we have a pair of verbs, and we have a relation that we're testing for. And for each relation, we have a set of patterns that we need to test. So then the question is, for a particular pattern, what is the association, the strength of association between the verb pair and that pattern? And the way we define that is as mutual formation as it sounds. So then between a verb pair v1 and v2, for a particular pattern p, then we define it as the joint probability of the three events divided by the events happening independently. So then we can get this score for each pattern on a pair, but we have multiple patterns. So all we do is we sum up this score for all the different patterns, and then we apply, it's not shown here, but we apply a correction factor because for some relations we have more patterns than others. And then we just check if it's greater than a threshold. And this threshold was just defined by, again, looking at these 50 examples that we tagged, and then optimizing this on those 50. It's very simple right now. So quick note, so getting this probability on the top here, on the numerator, this is pretty easy to do. We just have to actually check the pattern instantiated with the two verbs on Google and see how many documents had this, and divide it by the total number of documents on the web, which we can approximate pretty well. But the denominator values here are hard to get. So what is the probability of the pattern P when it's not instantiated with verbs? That's a little bit harder to get. So we used the same trick as how you estimate the number of words on the web we used here. So we used a small corpus of text and saw how many times that pattern occurred with any verb, and then looked at the ratio and scaled it up to what it would be on the web. And to find the probability of V1 and V2, we actually just looked for how often you see to the verb. So like the preposition to, just to force it to be a verb.
So, and you didn't have to do any other smoothing because the counts were really high.
We didn't do any smoothing at all.
But
Yeah.
the infinitive isn't always going to be a verb, is it?
The what?
The infinitive to run
No,
isn't
no,
always.
you might get errors. Yeah. So we could also estimate the verbs using the same method we did for the patterns on a small corpus. We could also do that, but we haven't looked at it. So I said that we do a little bit better on these asymmetric relationships, and the reason is because we can do an extra test on them. So the asymmetric relations like happens before and stronger than, we can add an extra test. So according to the previous score, if the score was greater than that threshold, we say that relationship holds. But for the asymmetric ones, we also enforce that the score on the inverse direction of the verbs is much lower. Okay, so this is what this ratio does. And that gave us a boost of about 9% on the accuracy. Okay, so how do we evaluate this? So what we did is, again, we had about 30,000 verb pairs that we queried our system to find the relationship. And these were taken again from this DIRT output. And how efficient is the system? So we can do 4,000 verb pairs per day on a single machine. That's because we issue about 40 queries per verb pair. And each query to Google takes about half a second to run. But because, again, of our limitation on the number of queries, we only have 25,000 queries per day that we're allowed on Google. So we're only able to do about 1,000 per day. So it took about 40 days to do this set. So then, for each of these verb pairs, we used our system to classify them according to the semantic relation. And the tag no relation is output if none of the relations score above the threshold. So then to evaluate it, we did a small test. We just randomly sampled 100 verb pairs. And then we had 2 judges look at each of the semantic relations that were output by the system. And the judges simply had to say yes or no, is this a correct relation? But after the fact, what we saw was that often the relation was, the judge would say, yes, this is a correct relationship, but I would have preferred if the system would have said something else. And this happened with the strength relationship. Because strength is a subset of similarity, if it is a strength relation, but the system outputs similarity, the judge wanted to say, yeah, similarity is correct, but I would have preferred if you would have said strength. So we did a second test. So we asked the judge to tell what is the most preferred answer. So there's a flaw here because it was after the fact. So these are the results of the system. So on the rows you see the judges' scores. And so the first column, tags correct, that's the task of saying yes or no, is the system decision correct. And the middle column here is the preferred tag correct, that's the second task.
What does preferred tag now?
That's the second task where the judge is asked not to just say yes or no, but to say, this is the relation I want for this pair. Does it match what the system said? So it's a harder task.
It's what they would do between the verbs without seeing what the system did.
If they only got to pick one.
If they only got to pick one, what would they? What is their? Because sometimes you can have 2, right?
Precede and enable, probably.
Sorry.
Temporally precede probably goes with enable.
Exactly. So and it actually can go with any one of them. So temporal precedence can go with any one of them. So if the system gets one of them correct, the judge might say yes, that's correct, but I would have preferred you would have said this and this.
And do they get to look at examples? Or?
The judges?
Yeah.
Beforehand, there was training. So they took the same sample of 50 that we had tagged and looked at those and just to get an idea of how to do this. Yeah.
Okay, no, but let's say that there is a test pair.
Yes.
And the system asserts a relationship.
Yes.
And let's say the judge isn't sure whether it's...
Oh, can they talk? No.
Can they look at the examples, let's say the Google search that you did?
Oh yeah, they could do anything they wanted. I don't know if they actually did that or not, but they were allowed to.
You can, sometimes when you look at a relationship, unless you can think of an example, it's not
Yeah.
obvious that
Yeah, so they could definitely query it if they wanted to. So again, happens before can occur with any other relationship. So on the 17 of the 100 relationships that we tested, that the system generated happens before, on just those ones we got about 68% accuracy. So for the agreement, oh sorry, is there a question?
Oh, I was just going to say, is it accuracy or precision? Do you include no relation as something to be judged? Or? It's
precision, which I call accuracy, but I'm not doing a recall evaluation, which I'll talk about why in a second. But we don't, yeah.
So if there's a similarity relationship, but in actuality, but you have no relation, then they don't want that wrong. You see that?
If the system marks it as no relation, but it should have been similarity, the judge will say that's wrong.
Okay, so they do see that.
Yeah. So the agreement on this task between the 2 judges, on the first task where you were just asked to say yes or no, the kappa was 0.78 and it was 0.72 on the second task. Again, that 0.72 is probably inflated a little bit. It's probably a little bit lower because of this flaw that they actually got to see the system output as they were doing it. But on this second task, if we looked at the 73 out of the 100 pairs that the judges agreed on, the system did better on these, which makes sense. These are the easier ones for the humans, are the easier ones for the system. So this table here shows the breakdown of the different relations and how well we did there. So I removed the enablement relationship because we didn't get enough results. I think we got 6 or so relations extracted. But you'll notice that the in the 30,000 verb pairs, we saw 6 enablement relationships.
So this is going to go slowly.
To find more enablements?
Yeah.
Well, so I'm not sure if it's because there just doesn't exist many enablement relationships, or is it our set of verb pairs, which was taken from this DIRT output, that DIRT just doesn't find these enablement relationships. So here you'll notice that the asymmetric relations like strength and happens before are the highest scoring ones because of this extra test. It gets about 9% improvement by being able to test this asymmetry. So these numbers are pretty rough, and the confidence bounds were estimated at about like 6%, so they're quite big. But it's more of a proof of concept level here that, yeah, these relations do exist on the web and they are extractable, but there are many, many ways that this can be improved by post-analysis on the network, and also by trying to learn these patterns automatically or assign more patterns manually. Yeah, forget that part.
What kind of patterns did you have for the enablement relationship?
Enable X and then Y.
Yeah, but I was thinking if you could just search for a large number of word pairs with one of those patterns and then choose the ones that might count and test the other relations.
That's how we got so we took some examples of enablement relations. We queried Google.
No, but your candidate set was pre-selected. What I was thinking is you could expand your candidate set by picking one of them and seeing if you get
If you want to search for and subsequently.
Yeah. Okay. So some conclusions. So these relations are available on the web, and they are extractable using some methods like we've talked about. But there are, again, many ways of improving it.
Wait, go back, please. The 29,000 are verb pairs which you tried or which actually you confirm they have one of the 5 relations?
No, some of these have no relation. So the system, one of the system tags is no relation.
And those which are tagged as relation from those 65% are correct.
Those that are tagged with a relation or with no relation, we get 65%.
So no relation is also a tag.
No relation is also
Well,
tagged.
what's the error breakdown between those two?
Excuse me, but no relation means that there surely isn't a relation. Is that right?
That's tricky, right?
Or is it just I don't know if there is a relation?
So sometimes the human just said, I don't know the relation. But we told the user to say, if you see a different relationship that we haven't defined,
Meaning other than these 5.
like cause or something like that, then put no relation. Because the system's not looking for that.
But is the bulk of the 65%
No.
those verb pairs which don't have any relation?
No, so I think it was something like 82, it's in the paper, something like 82% of the verb pairs did have a relationship.
82% of 29,000?
Had a relationship, at least one.
I see.
But you judiciously selected these pairs to maximize the likelihood of that.
Yeah, these are taken from an output like DIRT that has strongly associated verb pairs. That's why we use this output. We didn't want to get all the
I thought
relations.
from the numbers you were given before that it's very rare that you succeed
No.
in such a, like you had 17 cases and 5 cases.
Out of that,
17, for instance, right here.
that happens before, but whenever you see happens before, you can also have other relationships, right?
I understand that, but I mean, I was led to believe by silly. I jumped to the conclusion
That there wasn't many, that a lot of no relations.
because you had a number of
Sorry,
17.
sorry,
If you
okay.
had 17,000, I would have.
I see,
had a
okay.
different attitude.
Okay.
I see.
All right.
So this is a rare relation. The happens before is a rare relation.
Well,
And the
I
other
mean,
numbers are substantially higher.
similarity is the highest scoring relation. It's about 24%. Oh, come on. I thought I closed this thing. I'm sorry. This is amazing. Good thing I
Good thing
got the network.
I know.
All right, sorry.
So this is 29,000 out of what? 11.5 million.
11,000 times 11,000 pairs.
So I should get 3,400 verbs.
3,400 verbs in which we have 30,000 verb pairs that are looked at.
Okay.
Yeah.
And then possibly
But-
7 million out of which you
Yeah. But we only looked at, the verb pairs that we took were for verbs that were similar to each other in this DIRT system.
The hope is, though, if you have the whole web in a box, you can try all possible combinations.
Yeah, absolutely. So once we get this index at ISI, then we can do many more queries and run it on the cluster and be able to maybe not do 11,000 by 11,000, but
And
keep growing this.
65% correct. Is an estimate from sampling, or is it actually people looked at 29,000?
No, that's from a sample of 100 only. So the confidence bound is quite big. Yeah. Okay, so now the question is, once you have this, these sets of relations, or other semantic relations that you harvest, how do you get this at the ontological level? So we see that one of the relations that was discovered by the system, by VerboCean, was that surpass is stronger than hit. But the question is, which sense of hit is surpass stronger than? Is it the hitting somebody, or is it achieving something? And it turns out that it might be useful in inference to actually know which sense here this belongs to. If you want to add it into an ontology, you have to know which sense this is. So then the question is, or the idea that I had was, if you take an ontology like WordNet, if you could assign to each node in this ontology a grammatical template, a template of the behavior of this node in text, then you could, and I'll show you how, then you could do this disambiguation. But how do you get this ontology disambiguated? So in previous work, what we've done is we take, when we want to extract features for words, you look at a huge corpus of text, and then for each word, you look at its word that occur on either side of the word, and you use those as features. Or you take each word in the text, and you parse the text, and then you give as features for the words all the grammatical relationships that the parser found for this word. So we've done this second option of using a parsed text, and then extracting grammatical features for words. And the type of output that you get is this. This might be small, I don't know if you can see it, but the input to the system here was, what are the grammatical features that the word chair occurred in a 6 GB newspaper corpus?
Yeah.
Okay?
How long did later? This looks suspiciously similar to like Decaying Lens work.
Yeah, this is work that I did with Decaying.
Okay.
Yeah.
So,
The previous work is this, yeah.
so how should we read this?
Yeah, so that's what I'm going to get to. So this demo, by the way, is available off my website, but you enter any word you want, and then it queries the database and outputs all the features of this word. And the features are grammatical relationships. So for example, this here is a relationship that says verb, object, noun. So each of these features is a verb, object, noun relationship with chair. So you can have a chair, you can take a chair, you can throw a chair, you can hold a chair, you can use a chair, make a chair, and so on. So each of those that I said is a feature of the word, and this is the frequency of that feature in this text. Here, these are nominal subjects. So who is the chair? The director is the chair. She is the chair, and so on.
Hemingway is the chair.
Hemingway is the chair. It was seen in text 6 times. I don't know.
I mean, in his time, right, there was no chair, there were chairmen.
It's a different Hemingway, he's the chair.
It's a different
Could be a different Hemingway.
Different Hemingway.
So
Dudley Moore, though, is the Dudley Moore we all know, right? Or is there a different Dudley Moore?
I don't know. So the point is here that, so you get these massive, massive feature vectors that you can then use to find similarity between words. But if you look within the feature vector itself, some of the features are features of different senses of the word chair. So throwing a chair is the furniture sense of chair, but holding a chair is typically more the chairman sense of chair. But these are all mixed up here. And the question is, can we, for each sense that is defined in the ontology we're looking at, can we assign to those senses the proper features from here to the different senses? Can we disambiguate these features? Okay, so if you could do this, the idea would be, let's look at, this is an example from WordNet. And what you see, when you see these leaf nodes here that have this kind of white color, it's not coming out very well. Those are leaf nodes. These are the lexicals in WordNet. And these other guys here, these are concepts in WordNet. So you see that the lexical chair is a hyponym of the concept chair, which also has other hyponyms like stool and desk chair and chaise longue and things like that. So then the word chair occurs under the furniture tree and also occurs under the chairwoman tree. So then the question is, if we look at that feature vector from the previous slide, can we assign the proper features here and the proper features here according to their different senses? And if you could do that, there's all kinds of things I think you could do. One of them is disambiguate VerboCean, and that's the one I'll talk about. What else can you do? I think you could maybe disambiguate things like multi-word conceptualization. So you find a new word or a new concept. Where does it belong? Well, you have a grammatical behavior for these things. You just find your new word's grammatical behavior and attach it to its most similar node. You can maybe do word sense disambiguation. I haven't looked into it. You could personalize WordNet to a particular domain, to a particular text. So you could find the right coarseness level maybe. So if this is the proper coarseness level for stool, then these things should have features, and they should be similar but still different if you look at the feature vectors. If these don't have features, or if these guys have identical features, then essentially they mean the same thing. So we can say this is the wrong coarseness level, we should go to this level here. That might be a way of doing it. We could place a new word into the hierarchy. We can move a concept. We can discover that, I think it's petrol in WordNet, it doesn't seem to be in the right part. It doesn't seem to be like in the gas fuel part of the hierarchy. So you can notice that in text and say it's not similar to its brothers and sisters, but it's similar to this part of the tree over here, so let's move it. You can answer the question, what makes a chair different from a stool? So let me take out that point so I can show it to you. So how is a chair different from a stool? Well, we can look at how chair behaves in text and how stool behaves in text, and we know how its parent behaves in text. So we can just say, we can just look at all the features that are in here that are not there, and all the features that are here that are not there, and say these are the differences between the two, the syntactic differences between the two. Okay, the problem is how do we get these features? So the algorithm that I'm trying out, and this is current work right now, is a divide and conquer and a coup d'etat algorithm. Pen that. So the idea of the algorithm is, in the divide and conquer part, what we want to do is, I don't know if I should show this with a picture. Let me just show it like this. So in the first part of the algorithm, the termination condition of the divide and conquer algorithm is when you're at a leaf node, we just take the lexical features from text as we did in previous work. So in the previous work with my advisor, we just looked at how the word behaves in text, extract all those features. So we assign that as the termination condition in this recursion. If it's not a leaf node, if it's a concept in the hierarchy, then what do? Well, we recurse on all the children, and then we find in the children features that should propagate up to the parents. Okay? Now, how you actually do this propagation, there are many ways you can see how to do it. So then what you have, you can propagate features all the way up the ontology, but you still have ambiguous leaf nodes. So you haven't disambiguated it yet. So then what you do is the coup algorithm, the coup d'etat. So you go back down and you look at the leaf nodes, and then for this I'll show with a picture.
When you say common features, you mean literally overlapping features in the same count, or what do you mean?
There are different ways of propagating. So you might say if at least a certain percentage of the children have a particular feature, then we propagate that feature up, and we weight them in some kind of way. You might say, let's find a set of good representative elements for this concept, and then propagate their features up. Those are different ways of doing it. So
So you're not looking for, maybe you could look for a centroid of the vector.
yeah, that's what I meant by the second part. You can look for a centroid. So so suppose we did the divide and conquer part here, and then we want to do the coup part. So chair here and chair here are ambiguous. They contain all the lexical features we saw in text. But this concept here got its features by propagating from its children common features. And chairwoman here similarly got its features by propagating up the common features from here. So then how do we disambiguate chair? What we do is, to disambiguate this guy, we remove from its features, from its feature vector, all the feature vectors that occur in the parent of its other senses. So we look at the parent of the other chair here, and we remove the features that match the two. So we're sucking out that sense. That's the idea. And then you do the same thing for all the other senses of chair. And then you can repropagate up all the features again. So then you would get some disambiguated features. So this is all current work. I don't have any results on this yet. So I'm running out of time, so let me skip this part. So then, suppose you had this, this ontology that has disambiguated grammatical templates for each of its nodes. Then how can you use this to disambiguate things like surpass is stronger than hit? How can you know which sense of hit is meant in this relation? So what we do is, suppose you have a relation v1 rel v2, and you want to disambiguate v2. You can look at all the other verbs that the system discovered v1 has the same relationship with, and we call this set of verbs v. And we know how in text these words occur. And then we can just look at those feature vectors and find which vector of the senses of v2 in the ontology most match this set of verbs. So in a picture, this looks like, so if you want to disambiguate surpass is stronger than hit, so you have two senses of hit here. So which sense of hit is the proper sense for this relationship? We ask Verbotian, what else is surpass stronger than? And Verbotian says surpass is also stronger than overtaking and equaling. So then we can look at how overtake occurs in text, just lexically, you don't have to disambiguate it, and how equal occurs in text. And then we ask the question, for those two feature vectors, which of the two hit feature vectors are most similar to it? And the one that it's most similar to, that's what we assign as the sense of hit. Makes sense? Okay. So that's the idea on how to do the disambiguation. And I think I'll end there. And this is a final graph that the system found. And it's a path for how you can go from doing research to selling something. So you can do research and then design and then create and then develop and then patent and then license and then finally sell. There's another funny one that came out was you date, then you marry, then you divorce, and then you remarry. So it finds interesting things. But I'll... Kiss was also there, yeah. So I'll end there. Thank you. Yes.
So, actually, I've asked a lot of questions. Let me defer.
So I have a question about the way you were. Can you go back to 2 slides, maybe, where you have the there? So when you, I want not to say that you should do it this way, but I want to understand whether this would be a reasonable approach. Also, could you take the feature vectors remaining at each of the hit nodes, and then go back to Google and search your pattern again?
But I'm not actually using these features in the Google search, right?
Right, but you said you had v1 rel v2.
Yes.
Okay, so you're looking for surpass. So could you go back and do a search for surpasses stronger than hit?
Yes, but then you'd have to process the documents,
Right.
which we're not doing. So if you actually start processing all the hits that come back from Google, then it's really going to slow you down.
Okay.
So the only hits that we're interested in is the total number of documents that this occurs in. But it's definitely, if you start processing each of the documents that comes out, then you could do things like part of speech tag the documents, and you don't have to do these little tricks like having trailing V's in the patterns. And yeah.
So tell me again how you got the individual features from, let's say, this hit. Initially, they had all the same features, and
So-
then you subtracted out.
So hit has a feature vector here, and hit has a feature vector there, and after the divide and conquer part, these have the same vectors because they're taken from the text. Now, this hit here got its feature vector by finding the most common features of its children and propagating up, right? So you can imagine that if there are a lot of children here, the features that are going to be going up are not the ambiguous features. Okay. Same thing here, win gets its features by taking all of these children and propagating up. So then to disambiguate, let's say this hit over here, we then look at all the features that are in win, and we remove from this hit all the features that are also there. So essentially, all the features of the winning sense of hitting, we take out of hit here. And what's left are, there will be some noise, but the majority of the features that will be left are features of that sense of hit.
Okay, there are 5 of these hits, then you take out 4 of them.
You remove all the features that match on all 4. Yeah.
On any one.
On the parent of all of its other senses.
Yes. Not including this.
Not including its own self. So another way of doing it, at first what we did is we just took the features of its parent as the features here. But then you can't answer a question like what is the difference between hitting and falling and hitting. You don't have, they'll all have the same feature vectors of the children. It's not what we want. Yes?
If not for the speed considerations, do you think if you could parse speech data, would it improve? Do you have any results that show can improve your recall?
So I don't have results for it, but if you could part-of-speech tag, you wouldn't have these estimation problems. You wouldn't have to estimate as much. So we have to estimate how often the verb occurs on the web. We have to estimate how often the pattern occurs, and we have to do these tricks on the patterns to encourage the pattern to match on verbs. You wouldn't have to do that anymore. And you brought up recall, and I forgot to mention this. Recall is a good question. What is the recall of verb ocean? And I think it's really awful, but it's really hard to answer that question. One way of answering it is looking at the relations that we can discover that exist in WordNet, and then asking how many of the WordNet relations do we get back. And we did that, and it's horrible. It's about 13 or 14%. And then we did it the other way around. Then we asked, of all the relations that WordNet gets that we can get, what's WordNet's recall on our stuff? And it was 6%. So that either means that we're completely getting all the different things in the world, but I think what it means is that there's a lot of relations out there that we're both doing poorly on. So the recall is very bad. But we're not looking at every pair of verbs. And I think just by doing post-analysis on the network, we can find a lot of new relations because of these transitivity relationships. Yeah.
And the really important factor for recall is token, not type coverage. So if you can cover a lot of text with the relations that you have,
I see what you mean.
use a lot of the rare ones, it's probably not going to work.
That's a good point.
But you say you don't have any.
No, I don't have any numbers at all. Thanks.
So, surely you've thought about going beyond verb-to-verb relation. I mean, the obvious thing is to look at thematic relations between verbs and nouns. So you could distinguish, saw a man in the park with a telescope and stuff like that.
Yeah.
Because telescope is an instrument of seeing.
So we haven't touched that at all. So some people are grouping verbs according to thematic roles, like a pen and stuff. Some people organize verbs according to these hierarchies. We were just actually trying to relate verbs one to another. We've never looked
so
at.
I'm not talking about organizing verbs. I'm talking about relating verbs to nouns or nouns to nouns
sure.
instead of verbs to verbs.
Yeah. So
Which
we've
is different from what other people have done, I think. Maybe I'm wrong.
well, like at Penn, they're relating verbs to nouns, but not automatically. I don't know if they're doing it automatically or not. But we've done some work on noun to noun, so on finding is-a relations. And again, that's at the lexical level. But I think you could still disambiguate. So if you go to the example of chair, how do you disambiguate? If the system finds out that a stool is a chair, how can you disambiguate it? Well, you can look at how stool behaves in text and match it into this ontology, assuming stool is not already there.
I was also wondering whether you consider doing bootstrapping of patterns. It might be a little harder to do with Google.
To get more patterns?
To get more patterns.
So I think the approach that I mentioned that Deepak did last year with his biographical information, it was a bootstrapping approach. So you would give it seeds, and then by dynamic programming, find some patterns, and then test those patterns on new text, and do a sample of yes or no's, and then keep the high precision one, and then go again. Yeah. So I think that would be a great way of getting more patterns. It's clear that more patterns will help. We don't have enough. We have on some relations we have 3 patterns.
Yeah, it might be hard to do with Google, but maybe not. If you can analyze the documents when they come back, so you look for all sentences that contain both these verbs.
Yep. And then do
but
dynamic.
you don't have some relationship, and then see how it
Yes.
Am I wrong to guess that the sort of patterns you can look for are limited by the query language, Google's query language?
Yeah, absolutely. You can't look for punctuation.
Yeah, we talked about that.
Yeah.
So when you're doing it on the whole web, would a higher speed pattern matcher of some sort, more sophisticated one, would you be using something like that?
Well, you could get more expressive patterns, I guess. So the assumption is you could get better results if you could be more expressive in your patterns. So if you could, again, part of speech tag, you could be a lot more expressive in your patterns. Yeah, I definitely think that you could do better. So if we could crawl the whole web at ISI like we're trying to do, I think we'll be able to do a lot more better patterns. So again, this VerbOcean is available on the web if you guys want to download it. And if you guys have any ideas on how to clean it up or how to use it in a particular application. So how do you use this? We're not so sure. We haven't used it much yet. Maybe in summarization for reorganizing sentences in multi-document summarization, you might be able to use this happens before relation if it was cleaned up and you had a better coverage.
A naive question about Google. Is this, the fact that you can get this relationship, is this a side effect of their normal search, or is this something that they do on purpose?
that Google does on purpose?
Yes.
No, essentially it's a side effect, right? So you can use any indexing system you want if, as long as you can query. The richness is in the patterns. The point is that by searching these patterns, you can actually find these relations in text, semantic relations, as opposed to specific information like in IE, in information extraction.
So for example, if Google supported a query of the sort, these two words appearing within a 10-word window,
You could maybe use that.
then you would use it to, for example, find new patterns for the information
Absolutely,
search.
yes.
Because you know that these two words are in the same
Yeah.
sentence and you can bunch them.
So one thing we're looking at is alltheweb.com, which allows you unlimited queries. Alltheweb.com. Yeah. They allow you all the queries you want, and I think you can do a near query there, x near y, so it's within a few words.